Welcome everyone to this week's HoloTube seminar, and we have today Robert Myers from the Perimeter Institute, and we're very happy that he is going to tell us about complexity equal anything squared. Please, the floor is yours.
Okay, thank you very much. Well, the title is there. But I wanted to start by saying that I had a number of very smart collaborators that I got to work with. We put out a paper just the end of last year, and hopefully there'll be another one with some more details or an explanation in the near future. But you'll hear about that in today's talk. So if you've seen me give a talk in the past decade, you'll know that this is one of my favorite transparencies about holographic entanglement entropy. And so this is the idea that Shinsei and Tadashi Takiyanagi introduced us to, where we can, using the ADS-CFT, transform a difficult question about entanglement or entanglement entropy in the boundary theory to a geometric question in the bulk. And that, as it says at the bottom of the slide, became an interesting forum for a discussion, or where we were learning new things about both sides of the correspondence or the duality. We were learning new things about properties as strongly coupled field theories, but at the same time, we also learned some interesting lessons about holography and about quantum gravity in the bulk. And that really gave rise to a slogan that space-time geometry equals entanglement, or that it was saying that the quantum entanglement of the microscopic degrees of freedom were really a key feature for the emergence of a classical space-time geometry. And so it was a little bit disconcerting when a few years afterwards, Lenny Susskind came along with a paper that said entanglement is not enough. But if we looked at it more carefully, he really meant that entanglement entropy is not enough. And what he was pointing out is that that's really one measure of quantum entanglement, and that there are many measures. And in particular, he was interested in understanding, using these measures to understand what's going on inside of a black hole. And so this is just a fun picture. This is what we now know a black hole looks like, care of the Event Horizon Telescope collaboration. But today, all you're going to get is cartoons like this one that you're more familiar with. This is the Penrose diagram, of course, of an asymptotically ADS black hole. And what Lenny's interested in is then using some entanglement probes to understand the physics of this region where the green arrow is pointing. And just to illustrate why entanglement entropy is not enough, we can use an experiment that was first a thought experiment that was first put forward by Hartman and Maldacena, where what I'm going to do is I'm going to consider my eternal black hole. It has two boundaries, and I'm going to choose a region that's comprised of some degrees of freedom on the left side and some degrees of freedom on the right side. And I'm going to ask, what's the entanglement entropy of that set of degrees of freedom with the rest of the system, or the complement of A and A prime? And just using the standard prescription of finding extremal surfaces, one finds at, say, on this t equals 0 slice, that the Ryu-Takiyanagi surfaces actually stretch all the way across the Einstein-Rosen bridge, or as I've shown it on the right-hand side, there's actually two components coming from the n component. Well, if this was a two-dimensional boundary, there'd be two geodesics as I've drawn them, like that. Now, what we can do, though, is ask how the entanglement entropy evolves with time, and we push A and, oops, wrong way. We push A and A prime upward on the boundaries, and for a while, what happens is those surfaces are more or less the same. They're just stretching now. because of the extra space-time here inside the horizon. However, very quickly what happens is they snap back to another set of extremal surfaces, which are, well, they're kind of drawn in a funny way here, but what those are would be, if I considered A or A prime alone, those would be the Ryu-Takenagi surfaces. And so it's the pair of those now that form the global maximum that Ryu and Takenagi, Ryu and RT tell us to look for. And that's really something that was enforced by subadditivity. The entanglement entropy can't grow very large because it has to be less than or equal to the sum of these individual entanglement entropies. And so what's happening in this phase is that we're actually saturating this inequality. Now, these surfaces are entirely outside the horizon. In fact, they remain the same. The entanglement entropy is identical as we continue to evolve forward. And so we're not really probing at late times this interior region anymore. Now, you know, one of the observations one might make is that the entanglement entropy is a probe that knows about the eigenvalues of the corresponding reduced density matrix. So here's a standard formula. And what Lenny suggested is we want some new probe that's more sensitive to the structure of the density matrix. So in particular, it might be sensitive to the phases that appear in the time-evolved thermofield double. And his suggestion, of course, was the idea of holographic entanglement or holographic complexity. Now, I'm also going to change it and say holographic complexity as a question, because this may not be an idea that everybody's familiar with. And so I should give some introduction to what that's all about. And so we start with complexity itself. What is complexity? Well, it's an idea that computer scientists have, you know, thought about a great deal, and it's what it sounds like. It's how difficult is it to implement a task? You know, how difficult is it to run a physics institute? How difficult is it to organize a conference? Those are questions we might ask all the time. But today our question is, how difficult is it to prepare a particular quantum state? And we're going to use a quantum circuit model that's been developed by quantum information theorists. And it takes the form that I've shown here. We've got a reference state, and we're going to transform it into our favorite or our target quantum state. Now, the reference state, this psi naught, is, we should think of it as being some simple state. So for example, if it was a string of spins, we could start with the state where all of the spins are down. Typically, in this context, when we think of simple, we think of an unentangled state. So the basic degrees of freedom have no entanglement in the reference state. Now we want to transform that through by application of the unitary to our desired target state. But what we're going to do is we're going to say that unitary operator is built out of a set of simple gates that only act on a few of the spins or the few of the degrees of freedom at a time. And so there's some set of allowed gates that we put together then in a quantum circuit, as I've shown here. And the idea is, by applying this quantum circuit to our initial state or our reference state, we're aiming to get the desired state or the target state. Now, if I'm really doing this with discrete gates, as I've shown here, sometimes it's very, very difficult to get precisely to the state that we want, the target state. And so what's introduced is some level of tolerance, namely that if I get within some epsilon by some measure here, then I declare success, and we say that we've succeeded in producing the state that we want. What is the complexity then? Well, we think about all possible circuits that are achieving this transformation, and we want to find the optimal one, the one with the minimum number of gates. And then we simply count up the gates required in our optimal circuit, and that is the complexity, or that's one measure of complexity. Now, as I've described it very briefly here, there are a lot of abstract steps or choices where I wasn't very specific, and we'd have to adapt in a given question. And so, one question might be, is the answer that I'm going to get, is the number that I'm going to get for the complexity, is that going to depend on all of these choices? And the answer is yes. Now, that's something that we have to come to grips with, that the computer scientists have come to grips with, and they realize this. However, there are certain robust features that the complexity will show irrespective of these choices. And so, for example, they ask questions like, is it polynomially hard to do this as the size of the system grows, or is it exponentially hard in the system size? And so that's a robust question that they can answer, or it's a question with a robust answer. We're going to go beyond those specific questions, but again, a goal would be in our holographic setup to ask questions, find questions that have robust answers like this. Now, Lenny didn't just come up with this slogan, holographic complexity. He made some very specific proposals on what we might evaluate in the bulk to determine the complexity of the boundary state. And so there's two proposals here on this transparency. The first being complexity equals volume. There, what I'm doing is I've got my, well, in the case of my eternal black hole, I pick time slices in the boundary, and I've got a state that I can imagine is evaluated on those time slices. What I'm supposed to do in the bulk is I look very similarly to holographic entanglement entropy. I look at codimension-one surfaces that stretch across the space-time like this. I evaluate their volume. I find the surface that maximizes their volume, and then the volume of that surface gives us what I'll call CV, or that's the proposal for a measure of the complexity of the boundary state. Alternatively, on the right-hand side here, what we're doing is we have the same time slices in the boundary, and I look at a, if you like, it could be the causal domain of one of these boundary or bulk slices, or alternatively, I'm sending in light sheets to define a region of the space-time that's associated with these boundary times. And what I'm instructed to do is evaluate the action on this region of the space-time. And again, that's a proposal for how we measure the complexity of the corresponding boundary state. One of the things you might note is that sort of by design, both of these observables probe the interior of the black hole for arbitrarily late times, i.e. as I push T left and T right up in the diagram, I'll always, my observable, my gravitational observable will always be probing this region of the space-time. I'll also mention that some folks in Texas also suggested that, rather than evaluating the action in this particular setup here, we could also just evaluate the space-time volume that's associated with that region, or the Wheeler-DeWitt patch. And that also exhibited properties that suggested it's also an interesting measure of the boundary state complexity. So sometimes that's called complexity equals volume 2.0, or just complexity equals space-time volume. So those are some interesting gravitational or bulk observables. I've suggested that they have something to do with complexity in the boundary, but what is the story there? Why should I think these have anything to do with complexity? Well, there's a number of qualitative ideas that Lenny and his collaborators put forward, and so I'll run through those. The first one is a connection with MIRA, the multi-scale entanglement renormalization ansatz. And so this may be something that people know about, may not. It's not that important, but it's a particular representation of an efficient representation of the ground state wave function that was constructed by these folks here to describe two-dimensional critical systems, or if you like, two-dimensional CFTs. And one of the features that Guy Vidal noticed or showed in his construction is that this object is really a quantum circuit. You can imagine that I start up here with a string of spins that are all spin down, as I described in my in explaining complexity. Each one of these blobs then you can think of as a unitary or a gate that acts on a few spins at a time. And what it does is it takes the original state, this reference state, into some complicated entangled state here that is in fact the ground state of my favorite 2D Hamiltonian. So this object that's described as a tensor network, you can also think of it as a quantum circuit. Now, Brian Swingle realized that there's an interesting structure here that's really geometrizing the entanglement of this state down here. And he argued that, using arguments of entanglement entropy and how that worked, that this is really a discrete representation of a time slice of the ADS space. And so if complexity is something where I'm counting the number of gates in my circuit, that's essentially equivalent to evaluating the volume of this time slice. And so that makes a connection then between complexity in a very, in this discrete setting and a volume of a time slice. And so that was then the connection between complexity equals volume and this mirror idea. And so that's, again, you'll notice a very qualitative idea. Another one is that irrespective of which choice I'm making here, what one finds is that as I push the times to late times, the time rate of change of the complexity is a constant, and that constant is proportional to the mass of the black hole or the energy in the system. Now, why would you think that is a reasonable behavior for complexity? Well, this is something that Lenny and Adam Brown and others argued, again, a qualitative argument. I have a system with a large number of degrees of freedom, a Hamiltonian that's chaotic or has a chaotic spectrum. And what they argued is that when I'm evolving that in time, I can think that I'm putting down local gates coming from operations in the Hamiltonian, and I'm applying them to different degrees of freedom. And I'm more or less, because the system's large, I can think that I'm more or less throwing down these gates at random, acting on various groups of spins or degrees of freedom. And it's only very, very rarely that I'll get a cancellation where, applying a new gate will make that the circuit should actually be smaller because there's a cancellation between the new gate and ones that I've put down before. And so that I should expect that the complexity grows more or less at a constant rate as I throw down these gates with the time evolution. Now, what should the slope here be? Well, it should be proportional to the number of degrees of freedom. And they argue, or Lenny argued, that the entropy of the thermophile double state is a good proxy to measure the number of degrees of freedom that are relevant here. it's a time rate of change. And so I need to make up the dimensions though. And so he argued that the temperature is the natural scale to introduce, and that gives you a complexity that's extensive or proportional to the size of the system. And so then I would have that the time rate of change, or the slope here, is proportional to the product of the entropy times the temperature. But for a CFT, that combination is giving me the mass or the energy of the system. And so that agrees then with the result that we were getting from our geometric study, or for these observables. Now, I should say that this is only part of a much bigger story that Lenny put together in describing or thinking about complexity of these systems. It would grow for a very long time, and then it would more or less saturate. He expected as I explore the Hilbert space, I'm growing, but then eventually the complexity would saturate. There might be small fluctuations here. Eventually there might be recurrences. But all I'm going to be talking about today is this, with the geometric things that I'm thinking about, is this early stage where I'm seeing the growth. I'll add just in passing that there's an interesting paper by these folks here where in JT gravity, they suggested, or they found that by taking into account replica wormholes, that they argued that they could see this plateau in the complexity equals volume of the system. So that's the first two. The last one is the switchback effect. Here, what I'm going to imagine is I'm time evolving my thermophile double state, but I'm also perturbing it with operators, these W's. And I'm not, going to actually do this in a conventional way where you may think, well, I start at time 0, I evolve for a while, I make a perturbation, I evolve a little bit more, I make another perturbation, et cetera, et cetera. Instead, these folks instructed us to think about applying these in a zigzag order. So T1 is at a certain point, T2 maybe to the future of that, but then T3 is to the past, T4 to the future again, T5 to the past. And so the time evolution actually goes forward and backward in time as I scan through the operators here. Now, the interesting thing is that, well, for each one of these periods of evolution, what we found, or what we argued before, is that the complexity should be growing. And so the total complexity, should start to look like the sum of all of these intervals in between the operators. But what they argued, and I'll describe in a moment, is that there's actually a small shift here, that every time I do a fold, or I do a zigzag, there's a small amount of reduction that comes into this. So that in all, what I have is the total amount of time, and then this subtraction where there's the number of folds. For each zigzag, I'm doing a subtraction of this amount of time, called the scrambling time. That again is, the natural scale is the temperature, but it's proportional here to the log of the entropy of the system. Implicitly, I'm also assuming here that these intervals in each of the folds is much, much bigger than this scrambling time. So what's that scrambling time about? Well, let's focus on this fold here, the T3. So there's an operator I put in, or I'm using the Heisenberg notation where there's all of these time evolutions that are associated with the operators, and I think of them all as operators that may sit at t equals 0. Now, if I did not have that operator, then it's clear that the backward evolution here would completely cancel with the forward evolution with the e to the minus ht3 on the other side. And so there would be no, without that perturbation, there'd be no extra complexity associated with the time evolution down and back. However, if I introduce that operator down at the bottom of the fold, and I think that it's a simple operator, then which only touches a few degrees of freedom, I won't get a full cancellation, but I'll get a partial cancellation. The point is that just around after I do the switchback, or as I turn it around, that operator has only affected a few degrees of freedom. Its effect is not felt throughout the state. And so I'm still getting a lot of cancellation going on for degrees of freedom that are unaffected. But eventually the time evolution will, this small perturbation on a few degrees of freedom will spread and infect the entire state. And so at that point, then there is no cancellation, and I get the usual linear growth. But the idea of the switchback effect is then that I get a partial cancellation in the forward and backward evolutions as the effect of the operator spreads through the system, or as it scrambles in the state. Of course, on the gravitational side, that again is a qualitative argument, but you can find this behavior on the gravitational side by probing our black hole, by sending in shock waves, and you find precisely this kind of behavior here. And so that again is a match between the two. Again, a qualitative argument on the sort of boundary side or microscopic side, and the behavior observed of the bulk or the geometric objects or observables that we're looking at. However, one still has to ask, why are these the observables of interest? There's sort of this discrete choice that we're making. And these are really rabbits that Lenny pulled out of a hat, or our friends in Texas. And by examining them, they argued, or he and his collaborators argued, that this is displaying properties that we expect of complexity. But it's certainly true that we don't have microscopic derivation, say, in the same way that we do of entanglement entropy through the work of Maldacena and Lukowitz. It does have the flavor, though, of these ambiguities that I was talking about when I was talking about what complexity is and how there were different choices that we had to make. The difference here seems to be that there's a real discrete set of choices that I can make. And well, that's really setting the stage then for what my collaborators and I did in our last paper, or started to do in our last paper, where we were asking whether there's a broader set of choices that I can make for the gravitational observables. So we'll start by going back to complexity equals volume. And we'll notice that here's the formula that I described before, but there's really two independent steps that I'm doing here. The first one is this maximization of the volume on these surfaces. And by doing that, I'm picking out a very special surface in the bulk that traverses the space-time between these two boundary time slices. And then the second thing I'm doing is I'm saying, okay, given that special surface, I'm evaluating a particular geometric feature, namely the volume. And then I'm saying, well, that volume, that number that I get when I evaluate this quantity on that surface, is a measure of the complexity. But what it's really doing is it's a framework to build a nice diffeomorphism invariant observable. And so let's think about this more broadly. Let's try and generalize this idea. So our proposal is, let's start by thinking about step one. And what I'm going to do, or what we're going to do, is we're going to define some scalar function that I integrate over codimension-one surfaces. And then we're going to extremize that function with respect to where it's embedded, where the surface is embedded in the space-time. And this function, the scalar, can be a function of the background metric and of the embedding coordinates. And that means that, for instance, I can think of it as being a function that includes background curvatures, and I'll show you an example in a moment, or it could include extrinsic curvatures or intrinsic curvatures of that surface. But the idea is we choose a function here, we extremize it, and we use that to pick out a special surface in the bulk. Given that surface, I can choose to pick some other geometric feature of it. I can pick some other scalar function that I integrate along my special surface. And that then gives me a number, which gives me then, through these two steps, an interesting diffeomorphism invariant observable. But at this stage, you should say, so what? You know, you promised me a talk about holographic complexity. Here you're showing me that, well, you know, there's an interesting set of gravity observables, but what does that have to do with complexity? Well, this perhaps surprising thing is that what we were able to show is that for a very large class of these observables, in fact, at late times, the observables grow linearly with time, and that the proportionality constant here is proportional to the mass of the black hole. That's exactly what we found for these other observables, say for complexity equals volume. And similarly, if you probe the black hole or probe the observables with shock waves falling into our black hole, we find that they also exhibit the switchback effect, this small subtractions of the scrambling time. And so, in fact, all of these observables, or this broad class of observables now, display sort of robust features that we associated with complexity. And so it suggests that any one of them or all of them are equally good candidates for holographic complexity. So it's not just a discrete choice, but in fact, there's a whole family, or at least around complexity equals volume now, I've built a whole family of observables. And so I did want to run through one example. And so in this particular example, I'm going to use the same function for the function that we extremize and the function that we evaluate on the surface that we identify. And it's going to take this simple form here. The one, if that's all I had, I'd be doing complexity equals volume, because these integrals would just give me the volume of the surface. But I'm going to add a perturbation or an extra component that's proportional to the Weyl tensor squared. And I picked Weyl tensor because I could have stuck in Ricci tensor or you know, Ricci scalar, but those are just constants in the background of interest. And so this would have just been shifting the answer by an overall constant. This is something that, you know, varies in an interesting way in the black hole space-time that I'll talk about in a moment. And so this is a more interesting perturbation. And I've got here an L to the fourth just to make this dimensionless, and then lambda then is some you know, coupling constant that characterizes, it's a dimensionless number that characterizes my new observables. You know, as I hinted, I'm going to use this to probe a planar ADS black hole, and I've written down the metric here. This is the usual blackening factor, but I've written it in infalling or Eddington-Finkelstein coordinates. And so rather than using Schwarzschild time, I'm using these null time slices, the V. And I'm doing that because now my coordinates easily cover both the inside of the black hole and the outside, at least these two quadrants of my Penrose diagram. Remember, this describes thermal field double state, and we're talking about time evolution. It's really the sum of the two boundary times that comes into play here. You know, there's a symmetry. I can choose it, or I can set it up in different ways, but T left minus T right is not really relevant. And so I just set them equal to one another. And I've set, well, there's this coefficient so that what appears in the exponent is a single tau. And the idea is we'll set up our boundary slices and we'll push tau to infinity, which pushes us up to the top of the diagram. Now, if I evaluate my functional, I get an expression like this. This factor is just coming from the measure. Here, what I'm imagining is I've introduced a world volume coordinate, like a radius on this slice, a new coordinate, and I'm imagining that V and R have a profile, or they wander around in the space-time, and I'm measuring the position parametrically as a function of this new coordinate sigma. So this is another measure factor. This last factor is really the 1 plus C squared. Here's the 1. This is what C gave me, some power of R. And I've tweaked the lambda to just absorb a lot of factors of the space-time relation. Not so important. Now, having introduced this coordinate, I've done that really to give me some extra freedom. I can gauge fix it in lots of different interesting ways. A convenient way will be to choose sigma so that this measure factor reduces down to this factor here. And that's not immediately obvious, but I'm just using that while I'm building on experience from studying complexity equals volume. It turns out that's a natural thing to do. Another thing, building on past experience, is to think of this as an action that we're extremizing. So now I can borrow, my intuition from the classical mechanics books. And one of the things we know is that the time rate of change of the action is associated with the conjugate momentum evaluated at the endpoints of the interval on which I'm evaluating it. It turns out, well, the endpoint is now infinity, and there the Eddington-Finkelstein time and the Schwarzschild time are all identified, and so I can write this in terms of my V, and so the conjugate momentum then has a subscript V. Now that's interesting because in this problem here, there are explicit R's but no V's, and that means that this momentum is actually conserved. It has the same value at the endpoint that it does anywhere in the interior. And with this gauge fixing, it turns out that the conserved momentum takes this simple form here. So that's a constraint or an interesting feature of the problem. Turns out that this gauge fixing and that conserved momentum then allow us to massage the problem or the equations of motion and turn it into something that looks very much like a classical mechanics problem. This one right here, where I've got an r dot squared, a kinetic energy. There's an effective potential that's given by all of these factors here. And then there's an effective energy, which is just my conserved momentum being a constant. I just want to emphasize that, you saw P infinity earlier on. And what I want to show is that as I evolve in time, meaning boundary time, that this PV is more or less constant. The fact that it's conserved here is just saying that as I move in or along a particular surface at a given time, PV is a constant. So we'll see that this also remains more or less constant in time, at least at late times, in a few slides. In any event, here I've got this interesting classical mechanics problem. Again, it's something that I can use a lot of intuition from classical mechanics for. This is then a sketch of what the potential kind of looks like without the lambda term or without the c squared term. I get a potential that starts at 0, it goes up to some maximum, and then actually goes to 0 at the horizon and then heads off to negative infinity. When I turn this on, where I'm turning it on with a small positive lambda, turns out that essentially what I do is I pull this maximum up a little bit, but I also change the structure over here near r equals 0, because there's this factor that's blowing up as r goes to 0. So the potential turns around and heads off to infinity. Now, what are the trajectories? What are the solutions that I'm interested in? Well, I want a positive energy. It's p squared. So I'm up here somewhere. I'm going to start at infinity, so at very large r. And so the typical trajectory then is going to come in from large r. It's going to hit the potential at some point, and it's going to turn around and be reflected back out to infinity. And that's exactly in line with the pictures that I was drawing. I have a surface here, a candidate surface. It starts out at r equals infinity. It comes in, it reaches a minimum radius at some point in the middle here, and then it heads out again towards large r. And so the idea here that I come in from infinity, I hit the potential and go out, is precisely reflecting the kind of behavior that I'm seeing in this picture here. Now, there's this interesting structure in the potential, and so there's a family of trajectories as I go up, but something special happens here at this special energy and the special radius where the potential has a maximum. And in fact, the trajectory would come in and spend a lot of coordinate time around this maximum before eventually drifting in. And so that's a trajectory that comes in, it hovers around a particular radius for a long time before it heads off to infinity again. And I'll note that it's just some simple algebra to show that the value of the energy there, which is the momentum squared, is in fact proportional to the mass squared. So the special value of PV at this level right here is precisely proportional to the mass. I can also continue increasing the energy, and I find other trajectories that in fact pass that radius, go in even further, and then bounce out again. But really, to understand what's going on here, I also have, as well as sort of knowing what the surface is doing in R, I should understand, you know, where one of these trajectories, where one of these solutions actually hits the boundary. I have to understand what's the boundary time, and there's some more algebra one does, and the boundary times given by some integral like this, where I'm integrating from the minimum radius out to infinity. And there's some expression here that I have to evaluate. And if I plot that result for various values of P, I get a graph that looks like this. And so there's a set of surfaces here. Initially, I'm increasing. When PV is 0, I just go in, I run straight through the bifurcation surface and head out here. As I increase it, there are these surfaces that I've drawn. I get to a special point, this P infinity, where the surface is hovering around, you know, this special radius for a long time before it connects to the boundaries. And so in that initial phase, as I'm increasing PV, I'm sweeping through this family of surfaces. I can continue, and then I'm sweeping through another family of surfaces, the blue, where in fact they probe close to the, well, closer to the singularity than before. They pass the naive maximum. And in fact, if I push PV far enough, in fact, what I find is that tau becomes negative, which is curious, but the interesting point is that there's a dime reflection where I can actually attach these surfaces to an anchor point up here, so it looks like that. I didn't see this surface, the dotted line, in the original analysis because it actually leaves the part of the space-time that are nice naturally covered by my coordinates. but I can infer their existence from, these surfaces that connected at negative time. And so it gives this nice picture where for any given boundary time, we typically find there are three surfaces. One that actually heads to the white hole region, one that, this middle one, the red one, and one that actually probes the black hole or goes closer to the singularity. Of course, what we need to do is ask which one of those is actually the global maximum, which is actually the maximal volume or generalized volume of all of those. And it turns out that it's these initial surfaces. And so there are these extra surfaces, and later we'll ask, well, do they have a role? But for the immediate purposes of evaluating this generalized complexity, we just focus our attention on this initial set of surfaces. And one of the things we note is that for very late times, well, there's this pole or singularity in this graph. And so for very late times, PV is very close to this special value P infinity. And so for late times, the time rate of change is proportional to PV, which is more or less a constant, which is proportional to the mass. And so we recovered that first property that we saw that appealed to us about these gravitational observables. We can also think about the switchback effect here. I won't talk about any details. The analysis is similar to what we would have done for CV. The only thing we have to worry about are there, does this introduce any sort of delta functions or extra contributions when the surface passes through the shock wave? But the answer is no. And so we get both the linear growth proportional to the mass, and we get the switchback effect. And so, this is for our this family then exhibiting this robust behavior that we expect of complexity in the boundary theory. However, I can't say that it's an infinite family or it's a limited family, in that it turns out that this coupling can't be too large. When I rescale it by these factors of D's, turns out it has to sit in this particular range here. And so that's a curiosity that I'll come back to if I have time at the end. And there was also this observation that there are these extra extremal surfaces. That's already something that we've seen in holographic entanglement entropy, but we might ask, is there a role for these when we have a complete story? Or it may be that the complete story of holographic complexity finds a role for these surfaces in the same way that the extremal but not minimal Ryu-Taki-Nagi surfaces found a role in the story of holographic entanglement entropy. Well, I'll do that. There are actually lots of other things to say here, but I'm going to skip ahead and I'm going to think about codimension-zero observables, or what about complexity equals action and complexity equals space-time volume? Can we generalize those? In that case, it's not evident. We're not extremizing something as a first step and then evaluating something else as a second step. We were just given or told the prescription is think about the Wheeler-DeWitt patch. But I'm going to claim that, in fact, you can couch these observables in a broader family where we are actually thinking about it in this two-step process. What we're going to do is we're going to think about defining space-time regions where there's two boundaries for those space-time regions, a top and a bottom. And then again, we're going to evaluate some geometric feature of our codimension-zero region or our space-time region. And this is a way to come up with interesting diffeomorphism invariant observables. So here's my sketch. There's the space-time region. There's a top surface, sigma plus, and a bottom surface, sigma minus. Before I had two functions, and that's why I had complexity equals anything squared. now on this transparency, everything's going to go nuts, and there are going to be lots and lots of functions. In particular, to extremize or to find a special region, what we're going to do is we're going to say, well, I can evaluate some scalar on the top, another on the bottom, and I can also include some scalar or geometric functional that I evaluate on the interior, on the region itself. What I'm going to do then is I'm going to extremize the embedding functions for the top and the bottom, and that's going to identify special surfaces, special boundaries, and pick out then a nice region of the space-time. And just as before, though, I can, I could evaluate that same set of functionals, or alternatively, I can just come up with some new geometric functionals, including boundary terms for the top and the bottom, and a bulk term for the interior. And that's, again, a nice family of diffeomorphism invariant observables. But again, we should ask, so what? And it's quite a general feature, but I can say now, in many cases, I get these same two robust features: linear growth proportional to the mass, and the switchback effect for these new codimension-zero observables. And again, then they seem to be good candidates for holographic complexity. I just want to give one simple example. So this one, I'm evaluating the volume of the top, the volume of the bottom, and the volume of the bulk. And I'm adding them together, but I've added these sort of extra coefficients to weight the boundary terms relative to the bulk term. It turns out that's you can borrow analysis that, for example, Ed Witten, in fact, it goes back to Karl Kukash, who's thought about these kinds of or similar constructions, not exactly these. Turns out that the extremal surfaces are, in fact, constant mean curvature surfaces. That means that the trace of the extrinsic curvature is a constant. And in fact, that constant is determined by these coefficients that weight the boundary terms here. Now, the interesting thing to make connections with what happened before is, as the alphas go to zero, these extrinsic curvatures are diverging, but what we're doing is we're pushing the surfaces to become future and past light sheets. And so in that limit, the region that we're picking out with this prescription becomes precisely the Wheeler-DeWitt patch. So if I evaluate the same functional where I've taken the alphas to zero, exactly what I'm doing is I'm evaluating the space-time volume of the Wheeler-DeWitt patch. So I reproduce that prescription. Alternatively, I can evaluate another functional on this surface or on this region. And so the action, including the boundary terms, is a natural one to stick in. And that's then how you reproduce complexity equals action. And so that's almost the end, but I have a bit of time. I'll just say that the key story here is that, where we observed there were these discrete choices in holographic observables in the holographic complexity story, we're actually seeing that there are broad families of these observables, all of which have sort of robust features which make them viable candidates for holographic complexity. But I wanted to come back to this question where I pointed out that, there were bounds on how we understood, say, that lambda term, that I couldn't make it too big in the example that I looked at. And so what is that, what is that trying to tell us? Remember, this was the range for this particular value. And, what you can see here in the graph is that this is the effective potential. And if I go beyond the critical value, what's happening is I'm stretching, or I'm pulling the potential up, and this interesting structure, the saddle points, disappears, and I just get a potential that, you know, monotonically decreases as I move out in the radius. And you might ask, well, what's happening to this graph? You know, as I sweep through the conserved momentum, the values of the conserved momentum, what's happening to the boundary time, or the time where these slices get anchored on at the boundary? And well, it turns out that, you know, again, well, here we were seeing there was a singularity at a particular point. You know, if I go beyond the critical value, that gets smoothed out into a smooth peak. And as I exceed the limit by a lot, it very quickly, that peak shrinks down to be just a small bump. On the other hand, I can tune myself to have the coupling very close, you know, above the critical limit, but very close to it. And then that peak becomes very, very, you know, arbitrarily large, depending on how I tune it. Now, remember that basically, to look at the time rate of change, well, that's given by PV here. And so basically, I take this graph and I turn it sideways. And so I'd end up with a graph like this, where the time rate of change of my candidate observable, you know, it goes up very quickly, but then it remains a constant for a long time. So that looks like what we saw before, but then somehow our analysis just breaks down at a certain point, and I don't have an answer there, and that's just very strange. So let's go back to think about, you know, how can things disappear? They can't just disappear, or you might think that's odd. So let's think about a situation where we're beyond the critical value here, or well, the idea is we're going to think about the critical, going beyond the critical value, and we're anchoring our surfaces beyond the maximum here. You know, we know that there are lots of space-like surfaces that I can connect my boundary time slices with, and they'll kind of fill out the Wheeler DeWitt patch. No matter what surface I want, it's going to, you know, live in this blue domain. And in fact, there's that's an infinite dimensional set of surfaces. It can, you know, have all sorts of, you know, wrinkles in it as I sweep out, or as I, you know, think about candidate surfaces. But I'm just going to imagine sweeping across the Wheeler DeWitt patch here with a smooth set of surfaces, and that's like a one-dimensional slice of this whole infinite dimensional moduli space. And I can imagine, or I can ask, what is the complexity, or what is the associated number or observable going to be that's associated with each of those surfaces? And so when I'm just thinking about complexity equals volume, so I've set the lambda term, or I've erased the c squared term. Well, when I'm at the bottom of the Wheeler DeWitt patch on these light sheets here, the volume is 0 because they're null surfaces. I'm going to sweep through the interior, and I know that there's a maximum, there's an extremal surface in the middle here. But then as I sweep up towards the top of the Wheeler DeWitt patch, I get a 0 volume along the light sheet. I get a 0 volume along the singularity, and then a 0 volume along the light sheet again. And so I get this kind of structure in this slice through my moduli space. At the boundaries, it's a minimum, and there's definitely a maximum in the interior, and so we weren't confused at all. And yeah, that's just naming those points. Now I'm going to turn on lambda a little bit, and I'm going to do the same exercise. I'm going to have a family of surfaces, smooth surfaces. I'm going to take a one-dimensional slice. Again, down here, because the measure is 0 on the light sheets, in fact, the when I evaluate it, even if there is some finite contributions from c squared, I still get 0 at that point. As I start to sweep up, I approach the critical surface, and so I get an increase. The value increases to some critical point, and then it starts to decrease again. But I know that there's some saddle in here. There's some extra extremal surface. But then I know it after that saddle, it starts to blow up again. And that's largely because I know that c squared diverges near the singularity. And so I'm getting a very large contribution when my surfaces approach the singularity here. And in fact, if I've tuned things so that I'm beyond the critical value, then I don't, this structure of critical points disappears. There are no extremal surfaces, but I can still evaluate the generalized complexity, and it's going to, start at 0, and it's going to just go up and up and up. This isn't the effective potential that I was drawing, but it certainly looks very much like it. And sort of we were inspired by that. One thing you might worry is, well, it seems then for this family, I'll just say, well, the maximum is up here. But then shouldn't I have said that even in this case, the maximum is up there? And you might worry that the story I've been telling you about this critical point is actually not the right story to be telling. And I just wanted to assure you, first of all, well, in the case where lambda is negative, the story I was telling you is the right one. For positive lambda, it seems then that we maybe misidentified the maximum. You might ask, is that a problem or is that a feature? Currently, we're looking at it as a feature. It's an opportunity. What's happened is that the true maximum is sort of at the boundary of the moduli space. But the interesting feature is that it's probing the singularity. And so that's actually, for us, an interesting opportunity to study what's going on inside the black hole. And I've run a little bit over, but I'll just say, I hope I've given you a flavor for, holographic complexity and how actually, Lenny's pointing us towards interesting observables in the bulk. That story can be expanded to continuous families of observables. And perhaps that connects in an interesting way to the ambiguities that I talked about in defining complexity. And I'll just say then, or as the slide says, there are lots of things to explore. But at this point, I'll thank you for your attention and open it up for questions.
Thank you very much, Rob, for this very nice and inspiring talk. Are there questions?
Or is that an applause?
There was applause.
I have a question. So you mentioned that in diagonal entropies, there are these two competing embeddings sometimes, and there is some interpretation for the ones that are not dominant. What's that interpretation, and what do you have in mind in this case?
Well, they play a role in different places. There's a story that I think it was Jan de Boer, Vijay Balasubramanian, Bartek Czech put together about something called entwinement, where you look at in the boundary theory is a gauge theory, and you look at a more refined idea of what entangling which degrees of freedom with which. So that's one place where these surfaces have come up. Another is more recently in actually thinking about the complexity of operators. I'm thinking of Netta Bacall, Jeff Pennington, and I know they have collaborators and I've forgotten their names, but they were thinking about, how hard it is to reproduce bulk observables. And what they argued is that, observables sort of within the, or outs, outside of, meaning towards the boundary of the first extremal surface, not necessarily the minimal one, are relatively easy to recover in the boundary theory. Surfaces or operators that lie beyond that extremal surface are in fact complex or much harder, exponentially harder to reconstruct in the boundary theory. And so these extremal but non-minimal surfaces then play a role in separating easy operators and very complex operators in the theory.
Okay, thank you. And I had another question, if I may.
Sure.
So above this T max that you find, couldn't it be that the volume or this surface you are computing just split as it happens for the entanglement entropy, and then you have to compute the volume into different surfaces? But you don't see this because you are imposing this turning point in your prescription to compute the integral?
You're saying that out here there might be other candidate surfaces, extremal surfaces that I just haven't identified yet. Is that the idea?
In the same way that when you do entanglement entropy at some point, the entangling surface breaks, then you have to change a little bit the boundary conditions in the integrals. Maybe here there's something similar happening.
Yeah, it's not that you're changing the boundary conditions. It's more, I had a pretty picture somewhere like this one. You've chosen fixed boundary conditions, but what you do is you identify that in the bulk there are a number of different extremal surfaces, and well, this is an example where we identified a whole series of, or a number of different extremal surfaces, but then we had to ask which is the maximum, and we identified which is the maximum. So that's the same thing we did, or that's a lesson we learned from holographic entanglement entropy. In this case, or in the case where you're going beyond T max, it's just that if I set my boundary condition here, I can't find any surfaces, extremal surfaces, that make it all the way to the other side over here.
Mm-hmm.
It may be that there's a shortcoming in the way we set the problem up, but I think it's very unlikely. What I was arguing instead was that it's really just that we've pushed the problem to a regime where, the extremal surface isn't locally extremal. It's really that we're pushing it to the boundary of the moduli space.
Mm-hmm.
And that's really that's the way that we should interpret that. And I have to confess, I don't know of examples like that in holographic entanglement entropy, but it's sort of a natural thing if you think about it a bit. But it's not that it's a local extremum, but it's sort of an extremum within allowed configurations.
Okay, thank you.
Yeah.
Maybe as it's somewhat connecting to Hervé's question, I could interject a question on entanglement entropy. Depends on the states in which you evaluate the reduced density matrix. Obviously, it also depends on which states you choose to trace out. So holographically, that corresponds to, for example, calculating your minimal surfaces over a black hole background or an empty ADS background.
Mm-hmm.
And so I'm trying to see, so basically now I see two knobs to turn. So one, your complexity measures that you propose can or will depend on the states that you choose. So basically what kind of space-time you choose. Mm-hmm. And also So similar to how you would call a state thermal or not thermal for entanglement entropy. And then the second one is with what coupling you add which curvature invariance. Like your example was the Weyl tensor, and as you said, you could choose different couplings, you could choose different invariants to add. So I'm trying to, now this is why it's related, I think, to Javier's question. I'm trying to understand what that means in the field theory. So in a certain sense, can you somehow point to these features, what they mean in the field theory?
Well, the hope, although, you know, we're far from that at this point, and the hope is that, you know, in the field theory, we're thinking about building a microscopic definition of complexity along the lines of what I had in the original, or in one of the early slides. And so
and that definition depended on the states, if I may, right?
No, what it depended on was a reference state.
Mm-hmm.
And that was one of the choices.
Mm-hmm.
But I really want to think, just like entanglement entropy, I want to think of that as a tool that I can apply to any state in the boundary theory. So I can think about the complexity as a tool. I can ask, and in fact, it's important that, you know, the complexity of one state by itself isn't very meaningful. What's going to be meaningful is when I compare the complexity of one state to another state to another state. And so, for example, asking about the time evolution of the complexity, what I'm doing is I'm comparing, you know, many different states, namely the thermophile double at different times. But I would also want to think that this is a tool that I can use to apply, think about, you know, for the vacuum state, or for charged, charged black holes or ensembles where I have a chemical potential, or you know, some other states where there's other interesting things going on in the book. But the idea would be that, you know, the family of states is one thing. They all have interesting entanglement structures, and I want to have a tool that distinguishes the entanglement structures of all of these states. The knobs that I'm, you know, the couplings like the alphas here on this slide, those would be, well, the hope is that those would be like modifying my definition of the microscopic ensemble, or the microscopic definition of complexity. You know, I might choose slightly different gates. I might weight the gates, you know, in different ways. You know, I gave a very glib definition where every gate counted the same amount, but you might think that some gates have a higher cost than other gates. And so by tweaking the relative weights of gates, or as you say, there was the reference state, by tweaking, you know, some property of the reference state, I'm changing the definition of my tool, or I'm, you know, the microscopic details of my complexity. And I would hope that or the suggestion is that might be like tweaking the couplings or the parameters that appear in my geometric observable. So I hope that explains sort of the perspective that we have.
Yeah, thank you. Any more questions? Okay, if that's not the case for now, then let's thank Rob again. Thank you very much for your very nice talk and the discussion.
Okay, well, thank you. And yeah.
Somebody else has to stop the recording because
okay.
Matteo. Oh, okay, it's